So on Monday's class, we talked about some observations. These observations hold for this system as well. This is a speaker. There's nothing different between this speaker and the last one, except that this one works and the other one didn't. So we still have a large permanent magnet at the base. That's what makes this thing so heavy. If you have anything magnetic or metal at your desk or ferrous at your desk, you should be able to see that this will attach to that structure. Coiled wire inside the circle. In a circle, you'll be able to see that by pulling out the speaker cone. Spring-like mechanism attached to the cone. You'll see that this springs back to some sort of neutral position. And then the last observation that we couldn't get to on Monday, which we can now with this different speaker, is that if I flip voltage polarity, cone moves in different direction. Okay. All right, so then we went through and we had a few notes on Monday that we got into the Bly laws, which describes how it gives us a simplistic idea. We're not quite to how the speaker works yet. It gives a simple idea of how force can be applied to if we have a B field. So I don't think I labeled this very well as B before. So this is a magnetic field. In this case, it's going into the page. And if we have a current going through a wire, how force can be applied to a wire if we have this current going through a B field. All right, and we call this the Bly law, which you probably would have seen in your physics classes, your second year of physics, electricity and magnetism. It describes the basic idea of force applied to any conductor that's carrying a current. So it's Bly law. The other one that's going to be important is called the Blue law. This is based off of Faraday's principle, or Faraday's law. So a change in magnetic flux or just moving a coil through a magnetic field Okay, so if we move a coil through a magnetic field, if we do this in the appropriate manner, we're actually changing the area that's interfacing with this magnetic flux, and so that's going to cause, with something of a constant magnetic flux density, if we change the area exposed to that magnetic flux, and we're creating if we are moving a coil such that we are changing the way in which the magnetic flux density goes to the coil, we're changing the area at which it's going through. And so therefore you're changing the magnetic flux. And so we know from Faraday's law, this will cause a change in voltage. Okay, so another example of a simple generator, and we'll talk about generators briefly, but generators are just motors run in reverse. Similar scenario. So before, we had a case where we were deliberately running a current through this system. So the system is, we have a conducting frame, right? So this frame here conducts electricity, and then we also have this movable part that makes electrical connections here and here. And we are going to, in this case, deliberately move this coil, or this part of the frame in this direction. But before we deliberately put a current through this coil, we said, all right, which direction is it forced? Here we're actually forcing it to move. We're saying which direction will current flow or voltage potential develop. Same idea that we have then magnetic flux going into the page. Everywhere? Okay, so this magnetic flux density, B, is constant. Okay, so what I do, remember that, let's take a side here, remember that flux is equal to the magnetic flux density times the area it's interacting with. Right? Remember this. Then we have, if we keep a constant magnetic flux, but we change the area here, we're changing the flux. Right? Okay, so by changing, B can be constant, we change the area, flux changes. Faraday's law, the voltage is a function of the change, or d dt, of P, right? The change in flux. And so we can get a voltage to form in this. So in this case, we are changing the area, we're making it smaller. That means we are changing or increasing, so I guess we're decreasing the magnetic flux density, or the magnetic flux. This is going to cause the positive electrons to move in this direction, and the negative electrons to move, sorry, the positive charges in this direction, negative charges in this direction. We'll talk about this a lot more in terms of generators, but this is basically how a generator works. This is blue laws, which you probably learned about in your electricity and magnetism class. This L means that this is mutually perpendicular. Okay, so if we have more complicated angles going on here, then this law doesn't directly apply, but if mutually perpendicular, and by that I mean that the length of this wire along the length is perpendicular to the B field, which is perpendicular to the velocity at which this wire is going. Then we get force, or sorry, electrical voltage potential E is equal to BLU. All right. So B is the strength of the magnetic field, L is the length of this wire, and then U is the velocity at which it's traveling. So in summary here, so we can use a current to generate a force. Okay, so that was the case of putting a current through a wire in a magnetic field. Okay, so this would create movement. Of some form. So this discussion is restricted to electromechanical machines. That's the purpose usually. We're trying to create movement in the system. This would create movement. This movement will also generate an electric potential or voltage potential. All right, and this will be a fundamental power loss mechanism in motors. Okay, we'll talk about this at length, especially with generators, but what slows the motor down usually is not viscous friction. It's actually the fact that you have this voltage potential that is built up in this coil when moving it through a magnetic field. We'll talk about that at length. Any questions on those ideas? Yes? So E is the voltage potential generator. So E would be, in this example, the difference between the voltage here and the voltage here. All right, so example. All right, so this diagram here may not look like it at first, but it is essentially the speaker that's being passed around the room. Okay, so what we have here, this drawing here is a cross section. So we have a case where we have this big permanent magnet on the back end. Okay, so this permanent magnet, if we were to look at it, if we were to say strip off the speaker cone and the coil, etc., and just look at it from this view here, so looking at this direction, we would see that we have a circular permanent magnet. We have, it could be flipped polarity. In general, I'd just say we have a north permanent magnet, north side of the permanent magnet around the ring, and in the middle we have the south side of the permanent. Okay, so that's the big heavy piece at the base of the speaker that's being passed around. Right, if you pulled out the coil, or you pulled out the cone, you looked at the coil that's on the inside, what you'll see is that you have this coil of wire, and this is going around the south pole of this permanent magnet. So it's going around the south pole and it's inside the north pole of this permanent magnet. So what we have is we have a circular system. At all cases, we have the coil of this wire that is perpendicular to the B field that's happening. So we have a B field going from north to south caused by the permanent magnet. As we've seen before, if we want to get the highest force, we make sure that the current is running perpendicular to that B field. And so the engineers who made this speaker were smart, and they made sure that the coil current would always be going perpendicular to this B field. And so then we have leads that then lead to the back. If I didn't mention this, but if you look at the back, you'll see that these two little terminals, that is what I connected the microchip to drive the voltage. So these would be leads, and if we have a voltage, we can then drive a current in this coil. This speaker cone, we can say, has a mass associated with it. It has some sort of spring constant associated with it because you can see it kind of springs back into place. And then it has losses. And so losses, essentially viscous losses in this case, are represented by B here as a stamp row. Okay, so that would be an engineering schematic of what's going on in that speaker. Any questions between the mapping of what was passed around the room and this diagram? Okay. Okay, so first question. So we have the case of, say for instance, we have voltage such that this lead here is positive and this lead is negative. So that means we're going to have a case of current going into the page here and current coming out of the page at the top side. So my question is, what direction is the force on this, this speaker cone? So with convention drawn, what direction is force on speaker cone? Everyone has their right hands up. Yeah, some people point this way. This way. People point this way. So we have the B field, right? So in this direction, that's my fingers. Current on the bottom side going into the projector screen, and the palms in the field. Right? Forces in this direction coming from the coil and bottom. Looking at the top side, they have B field going down, current coming out of the page, comes out of the palm. Right? So both the top, so both the bottom and the top, you're in the process of forcing this back to the right. Right? And then you can now start to wrap and think about this in 3 dimensions to understand this as well. So say, for instance, this example here. Some reason. Okay, back to this. Okay, so let's take a look at, maybe it's easier to see here, right? So if we have the case of, this is a loop, right? So if I'm looking at somewhere out in space here, I have current going around in this direction, so that means that current's going down, right? I have then still B field in this direction, still forcing. So every part of this coil, well, every part of this magnetic flux and the current going in this coil is causing this speaker film to be pushed out. Right? Now when I retract it back, then I have to flip the polarity of this voltage, and then I'll then force it in the other direction. So if I flip the polarity of this voltage, just walk through this exercise here. That does not change the magnetic field at all. That's constant. It's coming from a permanent magnet. Now, the current here is coming out of the board. So I have a case of B field in this direction. My thumb is the current coming out of the board. Force it to the left, and then we can do the same argument at the top as well. Right. So that explains why, if we flip the polarity, as you observed here, on this voltage source, we have different movement of this. Right. Any questions about the general relationship between the movement of the voltage applied and the movement of this speaker system? Yes?
We're not clear about the magnetic field induced by current.
So, yeah, that's a little bit more complicated scenario. The one thing that we'll say here is, at least in the general vicinity, it's going to be, so it's going to be perpendicular to this B field. Right? So if we look at, say, for instance, this is current into the board, right? It's going to create this magnetic field that runs in this direction. That's perpendicular, and so that's actually not going to cause an appreciable, let's think about that. Yeah, we have to look at it very close to this wire here in what direction it's going to be. That's a good question. I have to think about that more. But it's going to be perpendicular to this B field. All right, so in terms of looking at this problem, the statement here is plot the Bodie plot. And so the Bodie plot is going to be U over V. So V is the voltage applied. So by Bodie plot, we are saying that we care about harmonic inputs, right? So this would be, for instance, if I were to put a pure tone into the speaker of, say, 100 hertz. Right, so a sinusoidal voltage into the speaker of 100 hertz. What is the velocity in time of that speaker tone? That's what we would be asking if we're looking at this. Okay, so with a lot of these systems, I think you probably got very comfortable in your dynamics class of drawing free body diagrams. And so you had free body diagrams. Maybe you had multiple masses, but you probably very rarely had electrical systems integrated with that system. Okay, so in this class, we are looking at systems integration. So we are quite often going to be drawing both free body diagrams to describe how the mass is forced and therefore moves, and also drawing electrical diagrams as well to then write equations of motion for electrical circuit. All right, so that's going to be kind of the norm in this class. If we look at our mass, and what we have here, we have a mass, which is the speaker cone. This is speaker cone. And I'm generically using the word speaker cone, but this is the speaker cone and everything that moves with it, right? So this coil that's around the speaker cone is moving with it. That all adds to the mass. They're all moving in unison. We have a magnetic force, and we'll get into what this force is in a second. But we said that this magnetic force is to the right in the current configuration that we're looking at. The configuration that we went through first, right? Positive voltage. And then we have a spring force. And then we have a damping force. So we have equations of motion. We're going to do everything in terms of velocity. So it's going to look a little bit different than typical Newton's laws, because I'm just going to take the first integral of Newton's laws to get in terms of velocity. First derivative. So we have mu dot. This would typically be mx double dot if we say x is position, but also we can say if u is velocity, that's mu dot. Minus bu minus k integral of u dt. And then we have to talk about then the force on the system. So then the force is given by Bly laws. Right? As we said, the force on a wire is given by BLI. L, in this case, if we're looking at a coil in a speaker system, it's just the total distance of that wire. Right? So we have, if we look at one loop of that coil, the distance of that wire would be 2 pi r. It's given by the circumference of whatever that coil is. This, if you look at, if you looked at the coil, you see that there's a bunch of windings, right? It goes around multiple times. And so then this would have n turns of that coil. This is coil radius. Number of turns. Okay. Any questions on that? How we integrate now magnetic force into a standard Newton's law? All right, so I think that should be something that's familiar to all of you. The next element is probably a little less familiar, and so we'll walk through this one a little bit more carefully here. So if we look at the elements of this electrical circuit, okay, so we have a few things. We have some way to drive a voltage, right? This is our input to our system. All right, so if we're looking at the Bode plot, we're looking at output over input. So velocity is output, input is velocity, so our voltage. So we have some way to drive the voltage in the coil. This coil is going to have a resistance associated with it because it's a length of wire. It's also going to have an inductance associated with it because coiled wires or any type of electrical conductor has a certain inductance associated with it. And then lastly, it's going to have another voltage supply that's from this blue law, or the voltage created by a coil moving through a magnetic field, right? Where it's often called electromotive force. If those of you who've worked with motors a lot, you've probably heard of electromotive force. So the way in which we represent this is we have a few different potential differences that happen in this circuit. We have the driving voltage given by the voltage source. So that'd be, for instance, if we have, this doesn't do AC voltages, but if we had some sort of function generator that could drive an AC voltage, that would be the harmonic voltage that we're talking about sending into the system. And so in terms of tying this electrical circuit to hardware you may see on the speaker going around the system, this would be outside the speaker. This would be something we connect to it. So you just draw a little dividing line. This is outside speaker. And then everything to the right here would be inside speaker. Then we have a few voltage drops here. One from the inductance of the coil. This is our standard schematic for an inductor. Remember, inductors have coefficient L on them for inductance. It's going to have resistance, as we mentioned. So standard form of resistor. And then we're going to have another voltage support source caused by the electromotive force, or the voltage caused by this coil running through a magnetic field. E, also called electromotive force. Or EMF. So those of you who worked with motors before, maybe someone just called it EMF, and they didn't really spell out what it means, or what it actually stands for, electromotive force. All right, and so then equations of motion for this, we are often going to use Kirchhoff's voltage law with electrical systems. That's most generally going to be the most convenient way of expressing these equations. So Kirchhoff's voltage law is they look at all the voltage drops across the system, and then they have to, in any loop, and you're looking, and they have to equal 0, right? So if I go and start at this point, we just call it, just say, fictitiously say this is ground for the time being. If I go from this location across the voltage source, so I have an increase in voltage of V. I then go across the inductor, and I have a decrease in voltage given by the voltage across an inductor, which is di dt. So I forgot to mention this. This is I. We'll get to that in a second. That's the current in the system. We have then a voltage drop across this resistor, minus Ri. And then lastly, we have a voltage drop going from the high side to the low side of this element that represents the electromotive force in the system. And then we're back down to here, so this should all equal 0. So then if I want to apply or add the blue law to this, it gives us this equation. All right, so the last thing I want to point out before we get to the quiz is how these are coupled. And so actually, just before I jump in that, any questions about what I did with the electromotive force, or with the electrical circuit? And we'll be going through a lot of these, especially when we get to motors. So if this is all very new to you, we'll go through a lot of examples. So just a comment on how these equations are coupled. So let me zoom out a second. Okay, so we have two equations of motion. We have equation of motion 1, and we have equation of motion 2. And these are not independent equations of motion. So we have, in the top equation, we see U in a few cases. That's the velocity of the speaker cone. But we also see I, which is the current running through the electrical circuit. Right? In the case of the electrical circuit, we see I pop up multiple times. That's the current running through, right? But we also see a voltage that's driven by the velocity of this mass. So these are coupled electromechanical systems that we're talking about here. So we are going to look at ways in which we are going to merge these two equations of motion to try and understand how do we get for a transfer function between voltage and velocity. Don't have time to do that today, but we will go through that on Monday's class. Any questions on that? So 1 and 2 are coupled through U and I.